Okay, I think we're ready to start. Welcome to the second day of our Novel Experiments Conference on behalf of Josephine, Anna Maria, and myself. For the first session this morning, we're going to go to particle accelerators where novel experiments are also being done. The first talk is joint with the High Energy Precision 21 program at KITP. It'll be Jamie Boyd on a novel set of detectors, the FAR detectors at the LHC. Jamie, the floor is yours.
Okay, thanks a lot. So thanks for the invitation to give this talk. And as Doug said, I'll be talking about a set of mostly proposed new experiments that can be added to the LHC physics program in order to try and increase the sensitivity for new physics searches at the existing LHC facility. So just to set the scene a little bit, so as you know, there's been excellent performance of the LHC accelerator and also the detectors, but yet the LHC experiments have not found any evidence of new physics. And this is, of course, frustrating. So beyond the standard model, long-lived particles are theoretically well-motivated and in some sense, less well searched for scenario. And so they may be one of the best remaining options for a new physics discovery at the LHC. So this is a little bit what these experiments I talk about are interested in. So the current existing LHC experiments, the big experiments like ATLAS and CMS, are putting an increasing emphasis on searches for these things like long-lived BSM particles. But there's also a number of dedicated proposals for new dedicated long-lived particle search experiments at the LHC. And this would be to try and increase the coverage for theoretically motivated new scenarios. So in some sense, these new experiments could be considered good value for money because although they will, of course, cost money themselves, they would be increasing the scientific output from the LHC, hopefully increasing the chances of discovery. And the LHC was, of course, something that was extremely expensive to build and is expensive to operate. So we should try and squeeze as much physics out of it as we can. Most of these new experiments are searching for neutral long-lived particles, which then decay into charged standard model particles. And this means that they all follow a sort of similar principle in how they would try and do this. But the proposals do cover a wide range of detector sizes and costs. So even though they mostly rely on the same sort of principle, there's a really big variety in the sort of size and cost of these different experiments. And so that means there's also a big range in sort of where the proposals are in terms of getting approval to be installed, where they are in terms of funding and readiness for being installed. Sorry, I'm just having one small issue with my Zoom. So yeah, this is what not to be. Sorry for this. Okay, so moving to the next slide. So just to briefly motivate why we should search for new long-lived particles in general and at the LHC. So this is a plot which is shown in many of these types of talks which try to motivate this. This is showing the lifetime of particles in the standard model as a function of their mass. And what you can see is that even in the standard model, there's a huge range of lifetimes that particles have, from basically stable particles to strongly decaying particles which have extremely short lifetimes. And what causes this spread in the lifetimes of these particles is mostly coming from approximate symmetries, which would, if they were true symmetries, would make the particle stable. But since the symmetry is an approximate symmetry, this means that instead the particle has, its decay is suppressed, and this leads to it having some finite lifetime. So, of course, the same type of thing can happen in beyond the standard model physics theories. And in fact, long-lived particles can very naturally occur in many of the BSM theories. So to give you an example of different ways this can happen, you can have weak couplings. So for example, in supersymmetry, you can have weak couplings associated with the weakness of gravity or with R parity violating couplings. You can have decays which are suppressed because of the phase space of the final state particles. Or you can have decays which have to go through very heavy mediator particles, which then also suppresses the decay. So that's an example that happens in split-SUSY, which is a type of model. And in fact, maybe more relevant for most of the detectors that I'll talk about today, the dark sectors, which are, of course, sort of new sets of particles which are associated with dark matter. So when you have a dark sector with light mediators in them, this naturally gives you weak couplings. So this is all because the mixing between the dark sector particles and the standard model is through loop processes, which give you weak couplings. And in fact, if your dark sector mediator is going to give you the correct dark matter relic density that's been observed, and the dark matter particle is light, then this also naturally implies that you have a weak coupling. So you can see that in this sort of sketch here, which I've stolen from Jonathan Feng. So this is showing the interaction strength versus the mass of a dark matter particle. And if you have very low masses, then in order to get the right amount of dark matter, you need to have very low couplings. And once you go to heavier masses, so the kinds of masses that the LHC was originally designed to discover new particles at, of order TeV, then you have order 1 couplings. So that was the top right of this plot is kind of what the traditional LHC experiments were expecting to find. And these order 1 couplings means that the particles are not long-lived, but they decay promptly. We didn't see any of these type of particles in the LHC yet, unfortunately. And so maybe the reason is that actually the new physics is light and weakly coupled. And these are the type of area where the new physics particle, the experiments I'm going to discuss today, become relevant. Another thing that's, of course, very important at the LHC is the fact that we can produce Higgs bosons. And the Higgs boson has many interesting properties, but something that's interesting about it is it has extremely narrow width of only 4 MeV. And this means that even for sort of things which are weakly coupled to the Higgs, they can still have a relatively large branching fraction because of the narrow width of the Higgs. So long-lived particle experiments at the LHC can be sensitive to the Higgs decaying to long-lived BSM particles, and there's room for this at quite a reasonable branching fraction. So at the moment, the limits on the Higgs to invisible decays from Atlas and CMS, the best limits are sort of at the 10% level. So 10% of the branching fraction could be going to BSM particles, which wouldn't be seen in the traditional searches, which is what you would expect from these type of long-lived particle decays. So that's a little bit of the theoretical motivation for searching for BSM long-lived particles. So what are the main ways that we want to design these experiments? So since what we're looking for is generally rare, an important thing to try and do is to really reduce the background as much as possible and really try to be background free. And the way that this is done is by putting in shielding and distance between the interaction points in the LHC, so where the collisions happen and where these new experiments are. So by putting in shielding and distance, you can suppress the huge rate of standard model particles which are produced in the LHC collisions and therefore try to make a background-free type of experiment. And so most of these experiments are what we call a sort of light shining through wall type of experiment. And so I tried to draw a sketch here at the bottom to give you an idea what this means. So we have the LHC collision here, which is producing a huge number of particles. I mean, the collision rate in the LHC is extremely high. But then we have a lot of shielding or a lot of distance or both, such that all of the standard model particles are absorbed in the shielding and don't make it to our detector. And then this red dotted line here is trying to suggest that we have a neutral long-lived particle. So this is the BSM particle we're looking for. It goes through the shielding and then it can decay in our detector based on the fact that it's got an exponential decay distribution. So we're not forcing it to decay, it just decays here because of its lifetime. And it decays into, in this case, 2 standard model particles. And we would look for this nothing in and 2 particles out with coming from a common vertex, and this would be the signature that we look for. Now, of course, it's not really true that none of the standard model particles produced in the collision would make it into our detector in this example, but if we have sufficient shielding, we can get rid of all the hadrons, and basically what the only particles from the standard model that should make it through here are muons and neutrinos. And of course, one of the challenges of these types of experiments is then to convince yourself that you really can suppress the muons and neutrino related background. But it's very important to have this shielding to get rid of all the hadronic background, which is huge at the LHC. So you also want to put your detector at an interesting place in the lifetime parameter space. And in particular, this should be complementary to the existing LHC experiments. So that generally means putting your detector further away than the size of the current LHC experiments, Atlas and CMS. And so the experiments I'll talk about are between tens and hundreds of meters away from the interaction point. On the other hand, of course, because what you're looking for is rare, you also want to have a good acceptance for these type of particles to go into your detector. So this means you have to cover a substantial part of the solid angle, which is, of course, difficult if you're very far away from the interaction point. And in some cases, instead, you can place the detector in a specific location, which gives you maximizes the flux of signal particles that will go into your detector. And finally, and possibly most importantly, the detector has to be affordable. And so in this case, what people have tried to do is take advantage of existing infrastructure in the LHC complex as much as possible. So for example, using unused tunnels or caverns or galleries or even spaces on the surface in order to be able to put your detector in this place without doing special civil engineering work, etc. You do get some challenges associated with trying to put detectors in places which weren't originally designed for this, but of course it does mean that you can save substantial money and time without having to dig your own detector location. Okay, and I also wanted to highlight that at CERN, this effort called Physics Beyond Colliders, which is a study group that's been set up at CERN about 5 years ago, and this has been extremely helpful in sort of helping to study the proposed new detectors and push them through. And so Physics Beyond Colliders has dedicated resources to look at things like civil engineering, installation of services for the detectors, integration and safety aspects. And this has really been, I think, fundamental in being able to get some of these detectors, these experiments up and running and for pushing for new ones to also be realized. The final sensitivity, so what kind of exclusion or discovery potential these experiments have, is a really complicated function of their location, the production process which produces the long-lived particles that you're searching for, how they can reduce the backgrounds and their acceptance. So this is something that you can't really easily sketch, and you have to run Monte Carlo simulations in order to assess this sensitivity. Okay, so now I just want to flash through a few of these proposed detectors, starting with Phaser. So Phaser is a very small experiment which is situated in the very forward region of the collisions in Atlas. You can see in this sketch here, so this is a sort of schematic of the LHC where IP is the collision point in Atlas, and the LHC goes in a straight line here for 270 meters, and then it starts to slowly bend away from this straight line, the collision axis, in order, of course, to complete a circle in 27 kilometers, which is the circumference of the LHC. When you're about 480 meters away from this interaction point, the collision axis is about 5 meters away from the LHC machine, and it crosses this unused tunnel called TI12 that you can see in the bottom of this sketch. And so this tunnel is where Phaser is positioned, and this allows the detector to be centered on this collision axis. And it turns out that this is a very good location for looking for certain types of long-lived new physics particle. This TI12 tunnel was an old injection tunnel when when the LHC tunnel was used for the LEP collider. This is how they injected electrons into LEP, but when they built the LHC, they used a different injection tunnel. So TI12 is unused, and Phaser takes advantage of the fact that this collision axis crosses this TI12 tunnel. So this is about 500 meters from Atlas, and it's a detector that's looking for long-lived particles, light particles that are produced in meson decay in the very forward region. So in order to realize this detector, we measured particle rates and radiation in this tunnel during 2018 running of the LHC and found that these are compatible with putting an experiment there. And what's kind of nice here is that a particle from the interaction point to Phaser goes through 100 meters of rock. So this provides this shielding from the standard model particles. And what you actually see in Phaser is a really low rate of standard model particles. So what's nice about Phaser is it covers such a small, it's only 10 centimeters radius in the transverse plane. So it covers a tiny fraction of the solid angle, 2 times 10 to the minus 6% of the solid angle. But 2% of the pi zeros produced in the LHC collisions are produced in the angular acceptance of Phaser. And this is just because of the way that the collisions work. You get a huge flux of standard model particles produced along the collision axis. And this means if you look at this plot at the bottom here, which is showing the angle which with pions are produced with respect to the beamline as a function of the energy of these pions. And you can see the Phaser acceptance, which is shown here. This is for 1 inverse attobarn. So in the run 3 of the LHC, we expect 150 inverse femtobarns, and this means we expect about 10 to the 15 pi zeros, which are produced in the angular acceptance of Phaser detector. And so even if you had a very rare decay of a pi zero into a dark photon or a similar dark sector particle, so looking at branching fractions of order 10 to the minus 10, you would still get a substantial number of these particles which would be pointing towards Phaser and could decay inside the Phaser detector. So another thing that you can notice from this plot at the bottom here is that the pi zeros which are produced in the Phaser acceptance have very high energies. This is 1 TeV of energy. So this gives them a big boost, and it means that the detector being 500 meters away from the interaction point still has sensitivity to interesting lifetimes and couplings of these dark photons. So in this plot on the right here, you can see the sensitivity for different luminosity values as a function of the mass of the dark photon and its coupling. So the lifetime is increasing when you go down in coupling. And you can see even with one inverse femtobarn of data, you get unique coverage in this dark photon parameter space. And with the full run-3 data set of 150 inverse femtobarns, you get quite a decent region of unique coverage from phasor. So this is just a quick sketch of phasor. So the particles are coming in from the right here. They decay inside this decay volume, which is inside a permanent magnet. And then you have a tracking spectrometer and a calorimeter at the back. And this can search for a dark photon signal. If the dark photon is now coming in from the left, it decays inside this first magnet into an E plus E minus pair. These are separated by the magnetic field and tracked through the spectrometer and then leave their energy in the calorimeter at the back of the detector. What's the challenge here is that this dark photon that's coming in has a mass of about 100 MeV and a momentum of about a TeV. So the E plus E minus are really produced on top of each other, and the magnet is needed to separate these so that you can see them as two separate particles inside the detector. So just to flash a few photos of the progress of phasor. So here you can see the calorimeter and the tracking detector. This is the magnet under construction. So phasor was able to move very quickly because it uses spare parts from other experiments. This calorimeter module is from LHC and the tracking silicon detectors are from Atlas. And what you can see at the bottom right here is the phasor detector installed in this TI-12 tunnel, which was the installation was completed in March 2021. And so phasor went from an idea in a Theorists paper in summer 2017 to an installed experiment a few months ago. And all of this took about 3.5 years. So this does demonstrate that these experiments can be implemented fairly quickly when things go well. Okay, there's an idea to extend phasor in the future to give it a bigger radius. So at the moment, the radius of the detector is only 10 centimeters. By increasing this to 1 meter, you would significantly increase the sensitivity to new physics particles that could be produced in heavy meson decay. So the decay of things like B and D mesons. This is because the B and D mesons are more spread out with respect to the beam when they're produced, as you can see in this plot here. And that means that new physics models, where the new physics particles come in the decay of these heavy mesons, you get much better sensitivity if you have this bigger detector than this R equals 10 centimeter phasor. And so there's a possible future upgrade to phasor to try and increase the acceptance in this way. Okay, so now moving to kind of the opposite of phasor. So this is a very big proposed detector called Methuselah. You can see a sketch of how this looks here. So this is the CMS detector in the bottom here on the LHC beamline. And Methuselah is a big experiment that would be installed basically on the surface. It's actually dug into a trench which is 20 meters deep. And the whole detector is 29 meters high and 100 by 100 meters in the kind of transverse plane. So it's a huge detector and it covers about 5% of the solid angle. And the idea here is that you could get neutral long-lived particles which would be produced in the interactions in CMS. They would go through 60 meters or more of rock, which acts as a shield, and then they could decay inside the decay volume of Methuselah, and the tracks that they produce would then be seen by the detector. So this is, of course, sensitive to particles with very long lifetimes because of the large distance between the interaction point and the Methuselah detector. So you can see here a sketch of the different types of background that you would expect for this type of experiment. So you can have muons from the LHC, which can then scatter. You can have neutrinos interacting in the air in the decay volume. You can have cosmic rays, or you can have neutrinos coming through the Earth. And people have studied this, and by combining very precise timing and also position resolution of the measurements of these charged particles, you can reduce the background to a very low level of about 1 background event per year. The current idea for the detector is to use scintillator bars with wavelength shifting fibers coupled to silicon PMs. And so if each bar is 5 meters by 4 centimeters by 2 centimeters, where you read out at both ends, and this gives the required resolution of about 1 centimeter in space and very good resolution, sub-nanosecond resolution in time. The Methuselah team have produced this test stand you can see here, which has been put on the surface above Atlas and taken data while LHC was running. So this is 2.5 by 2.5 by 6.8 meters high. And here they could measure the muon flux. You can see here the angle of the muons, and the orange here is muons coming from the collisions. And the blue is in fact muons coming from cosmic rays, which are bouncing off the ground and then going upwards. And you can see that the data agrees fairly well with the expectation. The way that the Methuselah could be realized is in this sketch here. So this is 100 modules. Each module is 9 by 9 meters in this plane and about 29 meters high. And it has tracking layers at the bottom and then at the top with the decay volume in the middle. This has about 700,000 channels. And the idea is that the trigger could be combined with CMS below, which could mean that you could use CMS as an active veto. So when you see an event in Methuselah, you could see if there was any big activity that was pointing in CMS towards Methuselah, and you could veto on this if you wanted to reduce your backgrounds. The problem with Methuselah is, of course, it's such a huge detector, 100 meters by 100 meters, that you really have to minimize the cost of the detector components in order to keep the cost under control. And that's something that is being studied at the moment. You can see here the sensitivity for an interesting physics mode. So this is a Higgs decaying to 2 long-lived particles. As I mentioned, this is something you can only do at the LHC. And here you can see the sensitivity as a function of the lifetime. And you can see that Methuselah has a significantly better sensitivity than the current best sensitivity from the LHC experiment, which is from Atlas. Here you gain about 3 orders of magnitude in sensitivity and in lifetime. So this is really a big improvement. So a new idea called Anubis is a similar idea to Methuselah. But here the idea is to make the detector smaller by inserting it into the shaft, which is above Atlas. So this is the shaft which was used to lower down the components of Atlas during the construction. It's 18 meters in diameter and 56 meters high from the top of the cavern to the surface. And by instrumenting this with tracking detectors, you would cover something like only 1% of the size of Methuselah, but still have a pretty good sensitivity to the similar new physics models. And again, you could use Atlas as an active veto by looking at activity in the Atlas detector that's pointing in the direction of this Anubis detector when you see a signal-like event inside the Anubis. And here again, you can see the sensitivity. It's a little bit worse than Methuselah, but it's much smaller, of course. And the sensitivity peaks at slightly shorter lifetimes, which is what you would expect since it's closer to the interaction point. And here's another proposed experiment called Codex B, which is in some sense a little bit in between Methuselah and Phaser. So it sits in the LHC. This is planned to be situated in the LHC interaction point. So it's about 25 meters from the interaction point in LHCb, where there's a room which is currently full of the LHCb TDAC system, and this is being moved to the surface during the current shutdown of the LHC. And so this room is being freed up, and you could put a long-lived particle detector here, which is called Codex B. Here, the idea would be a 10 times 10 times 10 meter detector, and you would put an active and passive shielding between the IP and this detector in order to reduce the standard model backgrounds. Here, the concept is to use RPC detectors with very good timing resolution in order to be able to see these neutral long-lived particles decaying to standard model particles. And because this is so close to LHCb, it would be really integrated into the LHC readout in a way such as another LHCb detector, which would give additional advantages. So here at the top, you can see the sensitivity. This is for a Higgs decaying to dark photons with different dark photon masses, a light one on the left and a heavier one here. You can see the Codex B sensitivity compared to Atlas is much better. It's not as strong as Methuselah. And you can see that it can cover both light and heavy cases of these dark photons. So the status of Codex B at the moment is that they are proposing to install a small demonstrator in this location, so 1/25th of the final size of the detector, which would allow them to measure backgrounds and to test the detector technology and the reconstruction. And the idea would be to install this during 2022 and take data during part of the next LHC run. Already they've measured background rates in this proposed location by installing some scintillator-based detectors. And this plot you see here is looking at the rate of hits in these scintillators as a function of the beam time in a collision field in LHCb. And what this shows actually is that the simulation is, the results are fairly conservative with respect to the simulation. So they see less backgrounds than they were expecting, which is encouraging for this type of detector. Okay, and the last detector I wanted to mention in a little bit of detail is Millican. So this is a detector which is a bit different than the ones I've said before, because this isn't really looking for a neutral long-lived particle which then decays. Instead, it's looking for a particle with a very low electric charge. So electric charge is in the range sort of 10 to the minus 3 to 10 to the minus 1 of the electric charge, and with masses in the range sort of 10 MeV to tens of GeV. So such particles can be produced in models such as dark QED, through processes which you see on the right here. So it's a kind of Drell-Young production process where you can produce these milli-charged particles. And you can see the cross-sections which are used in these studies in this plot at the bottom as a function of the mass. And here the detector is basically relies on scintillator bars which are pointing at the interaction point. And when you have a milli-charged particle going through these scintillator bars, it releases, of course, a very low amount of scintillation light. And these scintillation photons can be detected. And by having bars that are pointing at the IP, you can control the backgrounds, which mostly come from cosmic rays and the dark rate from the PMTs. So this detector is being placed in an unused drainage gallery close to the CMS cavern. So it's kind of above CMS, about 33 meters from the interaction point, and again shielded by 17 meters of rock. So you can see in all of these cases, there's a good shielding between the new detector and where the particles are produced. So here on the right, you can see this is what the final Millican detector is hoping to look like. So it's made up of these scintillator bars with PMTs on them. Here there's 3 sets of scintillator bars, and they're angled to point towards the interaction point in a detector that's final detectors 1 meter by 1 meter by 3 meters. And in fact, the team installed a small demonstrator detector, which you can see in the picture here, which is just made up of a few of these bars. It's 1% of the final detector. This was installed for LHC running in 2018, and it was exposed to 35 inverse femtobarns of data. And this is really useful for understanding the backgrounds and how you would use this detector to do physics. But it was actually also able to make a physics measurement. And you can see here, this is the sensitivity that you can see in terms of the charge of the particle and its mass. And this red line here is the result which came from this demonstrator. So this 1% of Millican that was installed in 2018. You can see it does have some regions where it's the most sensitive results compared to the existing limits, which are the other colored curves here. And then what you can see in green here is the expected sensitivity for the detector, which they will install for run 3 of the LHC. And then also the final sensitivity in the green dashed line, which they expect to be able to achieve with the full high luminosity LHC dataset of 3,000 inverse femtobarns. So this is a nice improvement over the existing constraints. So this slide just tries to compare and contrast the different proposals which I've mentioned in terms of where they are from the IP, the size that they are, and also then you can calculate the approximate solid angle that they cover, which ranges from times 10 to the minus 6% for Phaser to 5% for Methuselah, which interaction point they're in. So most of them are in either Atlas or CMS interaction points, which will both see 3,000 inverse femtobarns in the high luminosity LHC. Codex B would only see 300 inverse femtobarns because the luminosity in LHCb is about a factor of 10 less than in the other big experiments. Here I show what kinds of new particles they're sensitive to. And I also was brave enough to sort of categorize how expensive these detectors are. So I think Phaser and Millican are fairly cheap and probably cost of order 1 to 2 million. I think Phaser 2 and Codex B are probably in the of order 5 to 10 million bracket. And Methuselah, I've never heard a sort of real costing of this, but for such a large detector, 100 meters by 100 meters, I imagine this is in the many tens of millions type of area. One thing I did want to mention is that all of these experiments except Phaser don't have a magnet, and they just see this neutral particle decaying to 2 charged particles. And this means that they can't reconstruct the mass of the long-lived particle in a reliable way. And in some cases, this has been criticized as a weak point of these designs. The reason, though, is, of course, that there's just not enough room to have them, or you can't build a magnet that would be able to see this in a good way. Okay, then I just want to very quickly change tack and mention neutrino detectors at the LHC. So there's no neutrino detector installed at the LHC at the moment, but when we were studying Phaser, for example, we realized there will be a huge flux of standard model neutrinos that will go along the line of sight and could be detected with an appropriate detector. So here you can see the number of neutrinos that would traverse Phaser in run 3 of the LHC. So 10 to the 11 electron neutrinos, 10 to the 12 muon neutrinos, and 10 to the 9 tau neutrinos. And by sticking in 1.2 tons of tungsten, we would expect about 1,000 electron neutrino interactions, 20,000 muon neutrino interactions, and 20 tau neutrino interactions. So this is something that's quite interesting. And in fact, since then, Phaser has introduced a new subdetector to look for these type of interactions, which was approved in 2019. And there's a new experiment very recently approved called SND, which is again an experiment that will look for neutrino interactions from the LHC. So for phasor, we put in a small emulsion-based detector, which you can see here on the line of sight of the collisions in 2018 running, and it was exposed to 12 inverse femtobarns of data. And we've started to analyze this, and we see some neutral vertices, you can see some event displays of here, which are likely to be the first neutrino candidates for neutrinos which have been produced in a collider. The analysis is still ongoing, and these could also be neutral hadron interactions. So I wanted to just very briefly mention a very new idea, which is called the Forward Physics Facility, which is kind of an extension of what phasor is trying to do. So what we've seen when we studied phasor and phasor nu is that there's a lot of interesting physics associated with this very forward region of the LHC collisions. So when you really follow the line of sight of the collisions once the LHC bends away. And so the Forward Physics Facility is a proposed new facility which could house a number of experiments, including phasor 2. And at the moment, the CERN civil engineering experts are looking at ways that you could do this. So you can see in the bottom 2 ways, things that are being considered. One is trying to widen what's called the junction cavern of the LHC. So in this picture, phasor lies here. And if we could widen this cavern a little bit, we'd be able to have 50 meters where we could stick interesting experiments on this collision axis. Or a more ambitious proposal is to dig a new cavern. So here we would have to dig a shaft down something like 80 meters and then a cavern, which would again be on the line of sight of these collisions where we could put new experiments. So just to give you an idea of what you could do in such a cavern, so you could install a neutrino detector that would, if you had a 10-ton neutrino detector for the full 3,000 inverse femtobarns of the high Lumi LHC, this would expect to get a few thousand high energy tau neutrino interactions. Remember, there's only about a handful of tau neutrino interactions that have ever been recorded. And so with this, you could discover the tau antineutrino, you could constrain the tau neutrino EDM, and you could study tau neutrino interactions with heavy flavor. This is something that's pretty interesting. There's also an idea to put a liquid argon TPC detector in this forward physics facility, which could have sensitivity to dark matter scattering where the dark matter is produced in the LHC collisions. There's a plot here which shows that this is really quite interesting for probing the thermal relic, a region of the dark matter parameter space for a number of models. And another example is if you took the Millican detector and just moved it to this forward physics facility to be on the line of sight, you could significantly increase the sensitivity to milli-charged particles. This is just by virtue of the location, which has where most of these milli-charged particles would go. So this is something that's really quite interesting and is being studied by CERN at the moment. So just to show, this is this FPF, this forward physics facility. This is a number of theoretical benchmarks which are produced by the Physics Beyond Colliders group at CERN. And the forward physics facility would have sensitivity to all of these types of model with phasor 2 and this liquid argon TPC and this forward milli-charged particle detector. So that brings me to the end. So I hope I presented to you a few proposals for new far detectors at the LHC, phasor, Methuselah, Codex B and Millican. Unfortunately, I didn't have time to mention everything. There's a couple more which I go through in the backup. I think these new detectors are theoretically well motivated and they could really be good value for money to increase the physics reach of the LHC. As well as the BSM and especially dark sector long-lived particle searches that I talked about, these new experiments targeting neutrinos produced in the LHC are something quite new. And to date, no neutrino produced at a collider has ever been detected. So this really could open up a new regime in neutrino physics. And neutrinos produced at the LHC are in an unexplored high energy regime, which could make them particularly interesting. And so this forward physics facility I mentioned is a very recent idea which could allow multiple new experiments to increase sensitivity in several important areas. And just, I leave it there, but I leave some references here. I hope I'll be able to post the slides so people can look at these if they want to know more.
Oh, yes.
Okay, so that's all I had. Thanks.
Oh, thank you for that inspiring talk. I learned a lot. I'm an outsider, but I had no idea these things were going on. Let's see, I'm sure there will be questions and comments. Let's try raising hands at first and see if that's necessary. So please raise your hand. While people are doing that, I have a naive question. How do you suppress the neutrino background in most of the detectors that you described?
Well, this is a good question. So, I mean, normally we don't really ever consider neutrino backgrounds in collider physics. This is something which we don't think is normally important. And I think phasor is in fact the only, because of the location of phasor, which is really on this collision axis. This is where the neutrino beam, in a way, goes. So, of course, it's hard to suppress, but the main thing is to have little material inside your detector volume. So our magnets in phasor are filled with air, and there is, of course, a chance that you can have an interaction of a neutrino in the air. Probably there's more chance that you can have an interaction in the scintillators, which we have, and we believe we would be able to control this using the tracking detectors to see where the activity is coming from. In phasor, we have a calorimeter made of lead, 100 kilos of lead, and we do expect about of order 10, 15 neutrino interactions inside the calorimeter, which will be something that we need to understand how to suppress. So, but to my knowledge, that's the first time that a neutrino background is really significant in a collider-based experiment. So it's kind of a new regime in a way.
Yes. Okay, Lance.
And how about neutron backgrounds?
Yeah, so neutron backgrounds, I mean, the general philosophy, I mean, in phasor, for example, we have, the particles go through 100 meters of rock, and we have high energy muons. So any background is effectively associated with this high energy muon beam. So we have a scintillator in front of the detector, which will tag the muon. And studies have shown that basically if you get a muon coming into phasor, it will always be associated with this muon. So by vetoing events where we see a muon entering the detector, we will also veto events where additional activity associated with the muon is also entering the detector.
So neutrons from the primary interaction point are either thermalized by the time they get there. They're just not really a big problem.
Yeah, I mean,
for any of these detectors.
Yeah, well, put my cards on the table. I work on phasor, so I can speak strongly for phasor. For other detectors, this has, of course, been considered. But this is what I was trying to mention at the beginning, that generally you have a lot of shielding. So you have tens of meters of rock for most of these detectors between the interaction point and your detector. So I think this is suppressing the background from primary particles.
Good. Stefania.
Okay, hi. Yeah, thanks a lot for the nice talk. So I have a question about phasor nu. So can you tell us a little bit more about the physics opportunities for neutrinos there? I mean, what new measurements one can do and...
Sure. I did have a backup slide I'm just looking for, sorry. Yeah, so the primary idea for phasor nu is to measure the neutrino cross-section for the three flavors of neutrino in an unprecedented energy regime. So this figure here is showing projections of the sensitivity for the cross-section. So this is the electron neutrino, the muon neutrino, and the tau neutrino as a function of energy. And you can see for the electron neutrino, so in phasor we go up to above a TeV, whereas measurements are basically below 100 GeV. So we're looking in a really new regime. For muon neutrinos, the cross-section can be measured again between sort of 100 and 1000 GeV. Here, there is actually measurements from IceCube at the multi-TeV level. So here, our measurements should be able to sort of fill the gap between accelerator-based neutrino measurements and IceCube. And for tau neutrinos, we expect, there's relatively large uncertainties, but we expect of order 10 interactions. So there will be large uncertainties, but again, this will be at unprecedented energies. I did also include a slide. So this is what SND, which is this kind of rival experiment to phasor nu. It's situated in basically the same place as phasor, but on the other side of the Atlas interaction point, so 500 meters, and also close to the collision axis. It's slightly offset from the collision axis. The physics motivations they give for SND is to measure the cross-section similar to phasor, but also to constrain the gluon PDF at low X. So this is by measuring electron-neutrino interactions in their detector, which is basically in their angular spaces coming from charm decay. And so somehow this allows you to constrain the gluon PDF. They also want to try and measure lepton flavor universality in neutrino interactions and to measure the ratio of neutral to charge current interactions inside neutrino interactions in their detector. I think phasor nu can probably also do some of these things, although, yeah, I think maybe S&D are a bit more aggressive in what they claim they can do.
Okay, thank you.
So maybe you're measuring more the production than you are the cross-section. I would guess that the cross-sections are theoretically better understood than the the small x production.
This is a very good point. So in fact, we measure something which has in it the production and the cross-section, and we can kind of choose what we claim we're measuring and what we're assuming. We've had long discussions on this. So what we might be able to do is use cross-section measurements which overlap in energy with existing cross-section measurements to constrain the production, and then use this to extrapolate into the new energy regime. But you're completely correct.
But you're probably also extrapolating in the production at the same time, right?
You're right.
Yeah.
No, it's interesting stuff, and it folds into forward QCD. And in fact, interestingly, there's a huge interest from IceCube for these type of measurements because they can constrain very forward proton charm interactions, which are somehow super relevant for IceCube in a way that I haven't completely understood. But this is there is quite some interesting stuff here. So, but you're right, forward QCD definitely.
It is great to see the overlap with IceCube too. Yeah, totally different facility.
yeah, exactly. So it's very interesting. Actually, since we made these plots, we now hope to be able to link the Phaser new emulsion-based detector to the spectrometer in Phaser with a new tracking detector, which would allow us to tag the charge of the muon. And so when we made this plot, we were looking at the average cross-section of muon and anti-muon neutrino. But now we hope we would be able to make these two measurements separately by being able to measure the charge of the muon produced in the interaction. So that's, I don't know, we have to study if we can really do this, but this would allow us to make separate measurements of the neutrino and antineutrino just for the muon.
Anybody else? I feel free to speak up if you have any last minute questions here. I do have another naive question, Jamie. If you discovered any of these particles turning up in any of these experiments, of course, it would be a revolution. If you discovered a millicharged particle, that would really upset the whole theoretical apple cart, I think. You know, no more gauge theories, perhaps. So what interest and even pushback do you get from theorists on the subject of, well, you'll never find one of those?
That's a good question. I have to say I'm not super expert in this stuff, but I think I've seen this mentioned in the context of what they call dark QCD, which is like these dark sector type models. And so I'm not sure exactly how, I mean, it's for sure revolutionary, of course, but I'm not sure it's completely something that people push back as being totally impossible to happen. But maybe I take advantage of your question just to highlight this point I mentioned about the magnetic field, because when you said if we discover anything, then it would, of course, be a revolution, and that's true. And I think there is a little bit of doubt about these type of experiments because you can't measure the mass of the long-lived particle that's being produced. So most of these experiments, they're looking for nothing coming in, and then you see two particles which point to a common decay vertex, what we call a displaced vertex. And of course, what we would like to be able to do is measure the momentum of these two particles such that we could vertex them together and say the parent particle had a certain mass.
Yes.
And if we could do that and we saw a number of events and they all come from the same mass, this would be extremely convincing. And it would also tell us the mass of the BSM particle that we're producing.
Yes.
So one of the limitations of these experiments is that they can't do that. And I believe if they did see a signal, probably the next step would be to build an experiment that would be able to tell you the mass. And this would probably be needed to really claim what people could really claim as a robust result. So yes. I don't want to put too much of a damper on these things, but in my mind, this is a little bit a weak point. And of course, the reason is clear because these experiments are big and it's hard to fill a big space with the magnetic field in a reasonable way. So that's the issue. Actually, in Phaser, we do have a magnetic field, but I think we still suffer from the same problem because the particles coming in are so high momentum that we don't get sufficient bending to be able to really measure mass with a good resolution. So,
anything else?
So I don't think discovering millicharged particles necessarily overthrows gauge theory. I think it suggests that there is a massless dark photon that has some kinetic mixing with our photon. And then things that have a sort of normal charge under the dark gauge sector can look like they have a small charge under our gauge
I see. It's just a small mixing angle. Okay, my own ignorance. Thanks.
It's a kinetic mixing, so you can understand it if you have particles, heavy particles that are charged under both. You draw a one loop graph that turns one photon into another by coupling to both of these.
Right. Again, small mixing angle. Thanks.
Yeah.
Okay. Well, Jamie, thanks very much for a great talk. Please do upload your slides, and other speakers upload your slides too. They are chock full of information and lots of good references.
Yeah, there's also a lot of backup slides, but for me, it wasn't obvious, so I'll just send you an email to figure out how to do it offline. Okay?
Okay, that's fine.
Okay. Thanks a lot.
Thanks.